Hello everyone, this is Lecture 16 of ComSci 141, Undecidability and Intractability. In the previous video, we discussed Turing machine extensions, Turing machine programming tricks, Turing machine with restrictions and extensions, and the closure properties of recursively enumerable and recursive languages. Now, we will discuss undecidability and intractability. Okay, so let's start. So far, we have seen continuous improvements in terms of computers' performance. We have seen improvements in the memory, so from floppy disks to USBs to now you have your smartphones which has a lot of memory storage. We have also seen improvements in the processor, right? So from like the early computers with their really slow processors, and then you now have the like i7, i8, i9, and then you have the GPUs now as well for gaming computers, right? So we have seen continuous improvements both in the memory and processors, and this is due in part to Moore's law. So if you're familiar with Moore's law, it states that the number of transistors that you can put in a chip or an integrated circuit doubles roughly about every 2 years. Okay, so we can improve the capacity or the performance of a chip by double every 2 years. Okay, so the processing power continually improves through time. So you see here the graph of the number of transistors per chip from 1970s all the way up to the 2010s. Okay, so from 10 cube, which is about 1,000, now you can put about 10 raised to 9, okay, which is a lot. Okay, so there's now billions of transistors that you can put into your chip. Okay, and so this is the reason why we continuously have improvements for our computer's performance. So computers always have constant hardware and software improvements. Okay, however, even with these improvements, there are still some problems that no computer can solve. Okay, so some deceptively simple problems are unsolvable for a computer. So what are these problems? So there are some problems that are impossible for a computer to solve, like appreciating the beauty of a painting. Okay, so humans can do that, they can appreciate the beauty of a painting, but to a computer, a picture is basically just a bunch of zeros and ones. Okay, it's just a bunch of numbers, bunch of pixels. So it can't appreciate the beauty of a painting. Predict basketball game results. So although you can build models to predict results of a basketball game or any sport really, it does not work 100% of the time. Okay, it works most of the time probably, okay, but not 100% of the time, because well, a basketball game or any other game has a lot of variables or factors that come into play. Okay, what if one player is injured, or what if one player has a bad day and doesn't perform as well as he's been doing in the past few games, right? So the computer cannot predict a basketball game result 100% of the time, or predict the winning lottery number. Okay, because if there was a computer to solve this, then the lottery would not it would be pointless, right? Because you could just ask the computer to print out the winning lottery number, so the lotto corporation or association will be bankrupt. Okay, so these are just some of the problems that are impossible for a computer to solve, and this is because there's a limit to what can be computed and what cannot be computed. So it's called the limits of computation. So let's define a computer problem formally. A computer problem is given a finite string as an input. Okay, so it could be a very long string as long as it's finite, and the output is also a finite string, and the answer has to be objectively correct and definitive. Okay, So objectively correct, it's absolutely correct, and it's definitive. It's definite. Okay. So let's see if these problems are can be considered as a computer problem or not. Okay. Student's essay has more than or at least 1,000 words. So checking if a student's essay has at least 1,000 words. Do you think this is a computer problem or not? Well, it is, because you can just count the number of words for the essay, right? So a word can be defined as a string of letters that are bounded, or that has spaces in the front and in the back, at the back. Okay, so they are divided by spaces. So you can count the number of words, and if it exceeds 1,000, then it's true, otherwise it's false. So this is a computer problem. How about giving the grade that the essay deserves? So what grade does the essay deserve? Is this a computer problem or not? Well, it's not, because this is a subjective problem. Okay, so one teacher might give it a grade of 90, the other could give it a grade of 75. Okay, so it really varies from person to person. So a computer cannot also determine what grade the essay deserves. Okay, how about sum of two integers? Well, simple. This is a computer problem because the computer can always give you the sum of the two integers. How about calculating square root of 5? Is this a computer problem or not? It's actually not a computer problem, technically, because if we go back to the definition of a computer problem, it has to be objectively correct and definitive. So the keyword there is definitive. And square root of 5 is 2.23606 dot and so on. So there could be a lot of other numbers after that. So it's not really a computer problem, because a computer is only limited to a certain precision. Okay, but how about if we ask, can you calculate square root of 5 to a certain precision? Well, now this one is a computer problem, because you're only asking it to compute up to a certain, like say up to 5 decimal places or up to 10 decimal places, something like that. Okay, but if you want to actually get the square root of 5 value, the full value, the computer might not be able to do that, because the full value might have too many decimal values. Okay, so if we ask it to cap it at a certain precision, then that is a computer problem, because it will be finite. Okay, so yeah, that's a little exercise on determining if a problem is a computer problem or not. Now, we are now actually in the part of the theoretical computer science in ComSci 141. So theoretical computer science has two main branches. You have computability and complexity. For computability, it focuses on the problem, is it possible for a computing machine or a computer to solve this problem? So, can the computer solve this, basically? Whereas complexity focuses on the problem, how much resource does the computer need to solve this problem? So, for computability, is it doable or not? For complexity, if it's doable, how much time and memory will I need to solve the problem? Okay, so how much resource do we need? Okay, so that's the difference between the two. So for computability, we have certain topics like computation models, and we've seen some computation models already, like finite automata, push-down automata, Turing machines, and yeah. And we also saw Chomsky hierarchy, which is the hierarchy of languages. That's also a computability topic. Okay, so these are the computability topics that we've already seen so far. But the one computability topic that we will focus on today is undecidability. Okay, so that is the first half of our title, Undecidability and Intractability. So for undecidability, Of course, it's a topic in computability, and it asks the question, what can a computer solve? Okay, so it differentiates between decidable problems and undecidable problems. On the other hand, intractability, the second part of our title, is a topic in complexity. Okay, and it focuses on finding out what are tractable problems, or those that are solvable in reasonable time, versus those that are intractable. And intractable problems are those that are solvable in theory but takes too much time in practice. Okay, so we're already assuming that the problem is solvable. Okay, but is it solvable in reasonable amount of time, or does it take too much time in practice? Okay, solvable in theory but it will take too long. So that is the focus of intractability. Okay, so for undecidability, we have the two, decidable versus undecidable problems. So for a decidable problem, you basically have a decider Turing machine to solve it. And remember, a decider Turing machine has a accept and reject output, right? So it represents recursive languages. Okay? And if it's an undecidable problem, then there is no decider Turing machine to solve it. So it represents non-recursive languages. So these languages are the recursively enumerable that are not recursive and the not recursively enumerable. Okay, so let me show you a diagram to see what are decidable and undecidable problems. So for decidable problems, you have the everything inside the recursive languages. So recursive, context-free, regular, those are decidable because there is a decider Turing machine that can solve it, and it's guaranteed to halt or stop. Okay? For undecidable, those are the recursively enumerable one here that are not recursive. Okay? So the ones outside recursive that are in recursively enumerable, and the not recursively enumerable languages as well. Okay? This one outside the circles. So those are all undecidable problems. Okay, so now for decidable problems, we said that it has a decider Turing machine that solves it, and we know that the Turing machine has equal computing power with the general purpose computer. So a decidable problem has a computer program that is guaranteed to stop. Okay, so basically it can be solved by a computer. So decidable problems are solvable by the computer. Okay. Now this is somehow related to algorithms because if you recall the definition of an algorithm, it's a sequence of computational steps that transform input into output. A decider Turing machine is given an input and it's guaranteed to stop for all inputs, right? And somehow it also has an output of whether it's accepted or rejected. So you can think of a decider Turing machine as an algorithm. So if the problem has a decider Turing machine to solve that problem, then you can think of that problem having an algorithm that can be used to solve the problem. Okay, so you can just think of the decider Turing machine and the algorithm as synonymous. Okay, so yeah. So let's take a look at some undecidable problems. Okay, so since we're talking about undecidability, what problems are undecidable, or what problems cannot be solved by a computer at all times? So let's start with the halting problem. Okay, so for the halting problem, you're given a computer program P and some input I, and the problem is, does the program P stop when given input I? Okay, so if you feed the input to the program, will the program stop if you run it? Okay, so that's basically the halting problem. Seems pretty simple, right? But this is actually an undecidable problem. Okay, the computer cannot solve this for all possible for all possible programs and inputs. Okay, so let me show you some examples. So let's say that this is your program, basic for loop, which prints the items in the array. If you're given this input, well, the program will stop because you only have 3 items in the array, so it's finite. So you can just print these 3 items and it will be done after 3 iterations, right? Now how about this one? While x is less than 0, x is equal to x minus 1. So you're subtracting from x. If you feed it x is equal to -2, well, the program will not stop because it's already less than 0, and you're even you're subtracting 1 from it, so you're making it even smaller and farther from 0. So you start at -2, and then -1, it becomes -3, -4, -5, and so on, and then it's farther from 0. So this will always be true because x will always be less than 0, because you started at -2 and you're reducing it even more. So the program will not stop. It will enter an infinite loop. Okay. How about this one? If x is less than 100, x is equal to x plus 1. Well, this will stop because this is just an if statement, right? So is x less than 100? Yes, it is. So you add 1 to it and then you stop. So that's it. So these are just some examples of input, the computer program and the input that you can use for the halting problem. Now, let's try to assume first that the halting algorithm exists. So if the halting algorithm exists, then it would be a decidable problem, right? So let's say that there is a halt algorithm that takes in a program and an input as the input and outputs yes or no, whether this program will halt given this input. Okay? So this algorithm, assuming that it exists, will solve the halting problem. So let's say that we don't have any restrictions on the running time. Let's say that we could wait however long it takes for the halting algorithm to stop, as long as we get the answer eventually. Okay. So this is guaranteed to stop eventually because it's an algorithm. It's a decider Turing machine. Okay. And it will answer yes or no. Now, so the halt algorithm will have the program P as an input and input I also. And then the task is to check if P will stop given I. So this algorithm, if it exists, is actually very useful in testing software, because imagine that you're creating a software and then you have this halting algorithm, and then you feed a bunch of different inputs to the software and see that it will not crash or it will not get stuck on an infinite loop. Okay, so it's very useful in testing. The problem is, unfortunately, the halt algorithm does not exist. Okay, there is no such algorithm. So to prove this, we will use proof by contradiction. So later on, when we've already proven that it does not exist, that means that the halting problem is undecidable. Okay, so how do we prove that the halting problem is undecidable? So as we mentioned, we'll use proof by contradiction. So at first, we'll assume the opposite. So let's assume that halting problem is decidable. Okay, so if it's decidable, then the halt algorithm exists. Okay, so halt is guaranteed to stop and answer yes or no. Now, we'll create another program or algorithm called inverse halt, and it works like this. So it's also given a program and an input, okay, as the two parameters, and it will basically do the opposite of halt. So if halt program input is equal to yes, inverse halt will go on infinite loop. Okay, so if the program stops on this input, inverse halt will go on an infinite loop. But if it does not, if it says no, halt program input is equal to no, then inverse halt will stop. Okay, so basically it will do the opposite of halt. Okay, so what if we try to feed inverse halt to itself? Okay, so we'll run inverse halt, and then just blank input. So what will happen here? Okay, so let's see. So at the start, if you have program P and input I, if halt output is yes, if it halts on this program and input, that means that P stops on input I, right? Because halt said yes. And the inverse halt will do the opposite and go on an infinite loop. But if P and I is given no as an answer to halt, okay, that means that P does not stop on input I. And inverse halt will do the opposite and it will stop, right? But what if this time inverse halt will be our program, and our input will be just any blank string? So if it's inverse halt following this pattern, if halt says yes, that means that the program stops, right? You have the program stops here because the P stops on input I. So halt said yes, so inverse halt stops. But in this case, inverse halt will run on an infinite loop, because if it stops here, it goes on an infinite loop here. But we are saying here that inverse halt stops and inverse halt also enters an infinite loop, which is contradicting, right? Now, if we also see the other side, which is inverse halt on no, that means that the program inverse halt does not stop because it said halt is equal to no. Okay, but if inverse halt does not stop, that means that inverse halt will stop. Okay, so this is also contradicting because this is saying that it doesn't stop, and then here it says that it stops. Okay, so in both cases we saw a contradiction, and that means that the initial assumption that the halting problem is decidable is wrong, making the halt algorithm not exist at all. Okay, so making the halt problem undecidable. Okay, yeah. So if the problem is undecidable, then that means that there is no algorithm or decider Turing machine that can solve it for all instances of the problem. And this is crucial. It applies to all instances of the problem. That doesn't mean to say that you can not create an algorithm that will solve it for a few instances or some instances. Okay, there could be a specialized algorithm that will solve it for a few cases and not work for others. Okay, so you can create an algorithm or decider that will work for some instances but not all, if it's an undecidable problem. So maybe you can do a halt algorithm that is specialized only for loops or for while loops. Okay, so you can always check whether the for loop stops or the while loop will stop. But to claim that it works for all possible programs is not that's not true. Okay, but you can do it for some instances or for whatever problem that you want to focus in. Okay, so that's for undecidable problems. It's that no algorithm exists for all instances. Okay, but some algorithm could exist for some instances. Okay, so I hope that's clear. Now let's see some more undecidable problems. We'll introduce the 3n plus 1 problem. Okay, so in the 3n plus 1 problem, you're given an integer n as input, and the output is the number of iterations to get from n to 1 using the following transformations. If n is even, you divide it by 2. N is equal to n over 2. But if n is odd, you make it 3n plus 1. Okay, so let's see an example. Let's say 10. If n is 10, so from 10 is even, so we'll divide it by 2, makes it 5. 5 is odd, so we'll apply 3n plus 1. So 3 times 5 is 15 plus 1, 16. 16 is even, so we'll divide it by 2, 8. 8 is even, divide by 2, 4. 4 is even, divide by 2, 2. 2 is even, divided by 2, 1. So we have now reached our goal. So how many iterations did we have? 1, 2, 3, 4, 5, 6. So we had a total of 6 iterations for n is equal to 10. Okay. Now, why is this undecidable? It's because it's actually the pattern is really all over the place. Okay. So what if, for example, we had 100? Okay. So let's have 100 as our n. So if it's from 100, we divide it by 2, 50. This is also even, so divide by 2, 25. This is odd, so 25 times 3, 75, plus 1, 76. Divide by 2, this is 38. And divide by 2, this is 19. Now this one is odd, so 19 times 3 is 57, plus 1, 58. 58 divided by 2 is 29. This one is odd, so times 3 plus 1. 29 times 3 is 87. Plus 1 is 88. 88 over 2 is 44. Over 2 is 22. Over 2 is 11. And then this one is odd, so 33 plus 1, 34. And then 17. Then from 17 you have 17 times 3 is 51, plus 1, 52. Divide by 2, 26. Divide by 2, 13. Times 3, 39, plus 1, 40. 20, 10, 5. And then you have the same pattern here, 16, 8, 4, 2, 1. So there's actually way too many transformations for n is equal to 100, and in fact there's a total of about 26 iterations. So we really cannot predict if the the pattern actually stops, right? What if it's what if it was like 99 over times 3 plus 1? What's 99 times 3? That's how much? 27, 297, right? 297 plus 1, that's 298. Then 298 over 2, that is 149, I think. And then 149 times 3 is 27. This is 12, 14, 3, 4. 447, then plus 1, 448. So you went from 99 to 298 to 149 to 448. So it's oscillating, right? So from low to high to low to high to low to high. So the pattern is really unpredictable. So we're not sure that it will stop for all possible integers. Okay, so this one is undecidable. There's also another problem called the generalized halting problem. And in here, you're given a computer program P as an input, and the output is the input I for which P halts or stop. So earlier in the halting problem, we were given a program P and an input I, and check if the program will stop for I, for the given input. For the generalized halting problem, you're just given a program, and you're supposed to find the input for which this program will stop. Okay, so this one is also undecidable. There is no such algorithm that exists to solve it for all possible programs. Next is equivalence. This is also undecidable. So given two computer programs, P1 and P2, do they do the same thing? Okay, does P1 and P2 do the same thing? So this is also undecidable. Now, if there was a algorithm that that exists for equivalence, it would have been very helpful, especially for testing, right? Next is specification. Does the program do what it is supposed to do? Okay, so given that you have the specifications of your program or your software, are those specifications followed by the program? So you can actually represent the specification as another program, and you can boil this down to an equivalence problem. So your specification is program 1, and then your actual program is program 2, and then just check if they are equivalent. But since equivalent equivalence is undecidable, then specification is also undecidable. Okay, it would have been cool and it would have been really helpful if there was such an algorithm that existed, right? Because you can just automatically check if your software really matches the specifications that were written. Okay. Now next, malware detection. This is actually also another undecidable problem. So first, let us define what a malware is. So a malware does something that a user does not want to do. Okay. A malware could also delete files. A malware could also gather info from the computer. So it's kind of a spyware. It could disrupt other programs, making your computer useless. Or it can install without asking. So might be some kind of a Trojan. Or some combination of the above. Okay, so there's the term malware is actually very general, right? So it's hard to define what exactly a malware is. There's too many variants and combinations. So it's hard to specify it. Okay, it's hard to define it in a way that every type of malware is covered. So the current antivirus softwares only detects a small percentage of all possible malware. So only the known malware are being countered by the antivirus software. So the process is, if you find the virus, then you report it, you report the bug, you report the virus, and then the antivirus software will or the software creators will try to counter that virus. Okay, will try to disable what it's doing, and then after that, then it will be detected already. But what if a type of malware comes in? So then you'd have to update the antivirus software again, and this cycle continues. So really, the process of malware detection, or malware detection for all possible malware, is a never-ending cycle, because new type of malware can always be introduced at each moment. Okay, so and then you have other undecidable problems like, can a line of code in a program be executed? Can this line of code be reached, basically? Okay, so there's no algorithm for that. Is the given context-free grammar ambiguous? So we said that this it's not possible to check right away, no algorithm to check if a grammar is ambiguous, right? Does the two given context-free grammars generate the same language, or basically are they equivalent? So there's also no algorithm for that. Is the language of the Turing machine regular? Is the language of the Turing machine context-free? So in general, we know that the language of the Turing machine is recursive, but specifically, is it also regular? Okay, because it might not be. Or is it context-free? Because it might not be as well. Okay, so so those are undecidable problems. So that is the limit of computation. So there's just some problems that a computer cannot solve, no matter what the improvements are later down the road. Okay, so even if we improve the memory, even if we improve the processor, the undecidable problem still cannot be solved for all instances of the problem. Okay, so now, if undecidability focused on decidable versus undecidable problems, or which one are solvable versus the unsolvable ones, for intractability, it focuses on decidable and solvable problems. So you're already assuming that this problem is decidable. There is an algorithm for that problem. Okay, so it can be solvable, but you're focusing on tractability. So is it tractable or intractable? So basically, you're asking, is the running time of the algorithm acceptable or not? Okay, so if we have a tractable problem, there exists a polynomial time algorithm to solve it. Okay, so the algorithm runs in polynomial time, and this is generally what we refer to when we say acceptable running time. Okay, so polynomial time, like O of n squared, n cubed, and so on. As long as it's only in the polynomial power or polynomial factor. On the other hand, intractable problems have this property. So any algorithm that can solve that problem, no matter how clever it is, it will run in at least exponential time. Okay? So no matter how good the algorithm is, it will always run in at least exponential time. So it could even be more or worse than that. Okay, but at least exponential time siya. So this is what we refer to when we say unacceptable running time. So exponential. So 2 raised to n, 3 raised to n, and so on. So for polynomial times, usually you have the O of n, log n, O of 1, it's constant, O of n squared, n cubed, n raised to 10, although that's very unlikely. Okay, but those are examples of polynomial time. Okay, whereas for exponential, you have 2 raised to n, 3 raised to n, 1.1 raised to n. Okay, that's also exponential. And in general, polynomial running time is more acceptable than exponential running time. Now, there are a few edge cases, like in n raised to 10 versus 1.01 raised to n. This one is polynomial, this one is exponential, but this one is better. Okay, but those are very edge cases already, very unusual cases. Okay, so in general, in most cases, polynomial time is what you want. Okay, and besides, this running time rarely appears anyway as a running time. So there's not many, or if at all, programs that run in this running time. It's a very weird looking running time, 1.01. Yeah. So in general, polynomial is better than exponential. So now, to introduce intractable problems, I'll tell you the tale of 3 friends. You have Alice, who works in telecommunications, Bob, who works in biotechnology, and Carol, who works in finance. Okay, so what is their story? So first, let's talk about Alice's problem. So Alice works in a telecommunications company, and in each region of the country, there are telecom centers located in select towns or cities. And these centers are connected by cables, okay, and thereby forming a network. However, not every center is connected to each other, as it would be impractical and costly. So only some centers are connected. So let's say if we are in the Philippines, maybe, or maybe just in region 6. So if there's a center in Iloilo City, and then there's another center in Pasig, and then there's another center in Rojas, and then in Aklan, and then in Antique, in maybe San Jose. So maybe the one in Iloilo City is connected to Antique and to Pasig, but that's it. So it won't be connected directly to Rojas, because from Rojas can be connected to Pasig, and then you can just pass by that network. Okay, and then of course you won't connect Iloilo City with Aklan because it's too far. You can just have the connection from Capiz to Aklan, and as long as everything is connected, right? So the company wants to check network integrity. Okay, they want to check if everything is working correctly, if it's running. So they want to install monitoring devices on telecom centers that would check cables that are connected to that center. Now, there's no need to install monitoring devices on all centers, because some cables would already be monitored by some other monitoring device. Okay, so if you have 100 centers nationwide, there is no need to install 100 monitoring devices as well. Okay, so installing a monitoring device is expensive, so the company wants Alice to find a way to identify which telecom centers to install the monitoring devices to monitor the whole network using as few devices as possible. Okay, this cannot be solved manually because the telecommunication network is very big, so you need an algorithm for it. So let's look at a simplified version of the network. So let's say that there are 5, 6, 7, 8, 9 So let's say that there are 9 telecommunication centers that exist so far, and this is the network. Okay. If that's the case, then okay. So for example, we could install it in here, B, H, D, and then F. So let's see if everything is now covered. So from B, it will cover this one. From F, it will cover this one. From H, it will cover this line, and that's it, and this line as well. And then from D, it will cover this and this. So we have 3 lines that are not covered, right? This one, and this one. And we already have 4. So maybe if we add one here, and then one here, and then one here. So all in all, we installed how many? 1, 2, 3, 4, 5, 6, 7. So we had 7, which is way too much. So can we try to reduce the number of monitoring devices to install? Okay. So the minimum number of devices is actually 4 in this case. So where would we install that? So we can install it in C, here, E, here, G, and H. Those are 4. Okay, and that is because it will cover this center in C will cover this line, this line, this line, and this line. For E, it will cover F and H. For G, it will cover this line, and this line, and then for H, it will cover this line. So every line or every cable is now covered by the 4 monitoring devices that you installed in C, E, G, and H. Okay, so yeah. So that is the problem of Alice. Okay. So formally, that is called the vertex cover problem. Okay. So in the vertex cover, you're given a graph with n vertices, and your output is the smallest set of vertices. So you pick some vertices so that all edges are covered by those vertices. Okay, so that's why it's called vertex cover. So if we tried to brute force this, okay, so let's say that this is our given network. So you have 4 towns or 4 centers, and you can install you can either install or not in this center. So for the first configuration, you don't install anything, so that's no. And then in the second configuration, you can install only in D. Will that work? Well, it won't, because it can't cover the other lines. How about for only at C? It also won't work. How about only at B, only at A and D, A and B, A and C, A and B and C, B and D, and so on. So all possibilities, right? So in total, there are 2 raised to n possibilities, because for each node there are 2 options, yes and no. So for option for vertex A, you have 2 options plus 2 times 2 options here in B, 2 options in C, 2 options in D. So that's 2 times 2 times 2 times 2, or 2 raised to 4, which is 16 in total. So it has an exponential number of possibilities. So if you go through it one by one, then it will take you exponential amount of time. Okay, so it's not a good idea to brute force it. So number of possible solutions is 2 raised to n. So each solution also takes O of n squared to verify if all edges are covered, because if there are n squared, O of n squared number of vertices or edges in the graph, then you have to check if each edge is covered by one of the vertices in your set. So 2n to create the solution, to check all solutions, and then n squared to verify if that solution is valid, then the total running time is 2n squared. So it's even worse than just exponential, because for exponential this is 2n, and then it has the extra n squared factor, so this is even worse, 2n squared. Okay, so that is the problem of Alice in telecommunications. Next is Bob, who works at biotechnology. So Bob works in biotechnology, and his current problem is gene analysis. His team is currently studying which gene groups work together. So for example, if A is linked to B and B is linked to C, then genes A and B and then B and C work together, but not A and C because they're not connected. Okay, so if they have a connection, then A and B should work together, and then B and C, which also has a connection, also works together, but not A and C since they are not connected. So the task of Bob is to find the biggest collection of genes that are all connected to each other. So this collection can be considered as a cluster, where each gene can be used in place of one another. Okay, and of course this cannot be solved manually because there are too many genes and connections. So let's show a simplified version of the problem. Let's say that there are only 9 possible types of genes, and these are the connections. So A and B can work together, A and C can work together, B and C can work together. So what are the groups, or we call this the clusters of vertices? So you can have A, B, C here. This is one cluster, right? You can also have D, H, I here, because they're all connected to each other. Then you also have E, F, G. But is that the biggest possible cluster? Well, the biggest possible cluster has size 4, and that is BCEG. But before that, let me show you a counter example, an example of a non-cluster. So in this case, okay, so ECFG is not a cluster because if you have this one, E is connected to C, F, and G. So it's connected to the other 3. Same with G. G is also connected to the other 3, right? E, C, and F. However, F is only connected to E and G. It's not connected to C. So for a cluster to be valid, it has all vertices have to be connected to all other vertices. So since F is not connected to C, this is not a valid cluster. Okay. Now for our biggest possible cluster, that would be BCEG. So we have that one here, B, C, E, and G. Okay, so let's check. B is connected to C, E, and G. C is connected to B, G, and E. E is connected to B, C, and G is connected to C, B, and E. Okay, so every vertex is connected to all the other vertices, and that is the biggest possible cluster that you can find in this example. Okay, so that is the problem of Bob. Formally, this is known as the Clique problem. So as an input, you're given a graph with n vertices, and the output is the largest set of vertices that you can find, wherein those vertices are all connected to each other, and we call that the clique. Okay, now if you brute force this, you would also take O of 2n squared running time. So just like Alice's problem, which was vertex cover. So it's also not a good idea to brute force this. Okay, now finally, let's look at Carol's problem. So Carol works in finance, and her boss wants her to create an algorithm that will optimize their financial investments. They want to spread out the risk as much as possible, following the idiom, don't put all your eggs in one basket. So they don't want to invest in two things that are too similar at the same time. So for example, if they're already investing in silver, they probably don't want to invest in gold, because those are quite similar in value. So if the value of gold rises up, there's a high likelihood that the value of silver also increases, something like that, right? So they don't want to invest in similar things at the same time, but they also want to invest in as many things as possible. So they want to diversify their portfolio and also maximize it. Okay. This cannot be solved manually because there are too many investment options and complicated connections. So Carol also needs an algorithm for this. So let's try a simplified version of the problem. So for this one, we have the following investment opportunities. So you have gold, silver, copper. So silver and copper mining is of course related to silver and the copper, and then copper mining is related to copper, and then both mining businesses are related to the bank, and then silver and copper mining is related to industrial manufacturing. Okay, so in which items should Carol invest in, so that she doesn't invest in two items that are the same, but she wants also to invest in the most number of possible items. Okay, so the maximum number of investments possible is 3, and that would be industrial manufacturing. Okay, here we invest here, at the bank, and at silver. So this is valid because silver is not related to industrial manufacturing. It's also not related to bank, right? Now let's try if we could add one more to this one. Could we add one more? Now if we add gold, it's not possible because it's already related to silver, right? If we added copper, also related to silver. Copper mining related to bank. Silver and copper mining related to all three, so it's not possible. So 3 is the most that you can have for this one. Okay, so that's the problem of Carol. So formally, this is known as the independent set problem, and you're given a graph with n vertices, and your output is the largest set of vertices wherein none of the vertices are connected to each other. So it's like the opposite of Clique, right? So in Clique, you wanted to find the largest set of vertices where every vertex was connected to each other. In independent set, it's the opposite. You want the most number of vertices where every one of them is not connected to each other. So they're all independent of each other. Okay? And if we try to brute force this, it also takes O of 2n n squared. So it's also exponential, which is not good. Okay. So the bad news right now is that they only know the brute force way of doing things. And if they use the brute force, it has an exponential number of possible solutions, so it will take at least exponential time to run the brute force algorithm. Okay? However, since they were friends, they tried to tell each other their problems, and they found out that their problems were actually related. Okay, so let's say that Bob and Carol met up over coffee, and they tried to describe their problems to each other, and since both of them were students of ComSci 141 in the past, they remembered that they could apply like algorithms for this, right? So let's say that this is the problem of Bob for Clique, right? So this is for Clique, and then this is for independent set. Independent set. So this is for Carol, this one is for Bob. For graph 1, what is the largest clique possible? So the largest clique possible for graph 1 is B, C, E, F. So you have B, C, E, and F. That is because they're all connected to each other, right? B to C, B to E, B to F, and then F to C, F to E, and so on. And then C to E as well. So they're all connected to each other. So if you isolate B, C, E, F, you have B, C, E, and F. There's a line from B to C, B to E, C to F, E to F, B to F, and C to E. So they're all connected to each other, right? Now, how about the largest independent set in graph 2? Okay, the largest independent set in graph 2 is also B, C, E, F. B, C, E, and F. And that is because B is not connected to C, not connected to E, not connected to F. C is also not connected to B, E, or F. F and E are not connected to each other, nor to B and C. So none of them are connected to each other, right? So they have the same answer. Now, can you see the difference between graph 1 and graph 2? How are they related? So try to take a few moments to figure out how the two graphs are different. Okay? Have you figured it out? Graph 2 is actually the inverse graph of graph 1. Now, what does that mean? What does inverse graph mean? Basically, if in graph 1, A and B are connected, in graph 2, A and B are not connected. Right? So there's no connection here because there is a connection here. And in here, A and D are not connected, right? There is no connection from A to D. And that's why here, they are connected. So basically, in an inverse graph, if two vertices are connected in the original graph, then they're not connected in the inverse graph, and then vice versa. If they're not connected, they are connected. Does that make sense? So hopefully you can see that here. AB is not is connected here, so A and B are not connected here. A and E are not connected here, so that's why there's an A to E line here. DC is not connected in graph 1, so DC has a line in graph 2. So graph 2 is graph 1's inverse graph. And if you actually run independent set on the inverse graph of the Clique, then you have the same answer. Okay? So it's pretty neat, right? So this is the definition of the inverse graph. If two vertices are connected, it's not connected in the inverse. If it's not connected, then it's connected in the inverse. So the answer to the Clique is just the independent set on the inverse graph. Okay? So you can reduce the Clique to the independent set problem and vice versa. So a reduction is basically just a transformation of a problem into another. Okay? So if you want to solve independent set from Clique, just apply the inverse graph and then you can just solve it as well. So the good news is Bob and Carol can work together, because if there's an algorithm for Clique, then it will also work on the independent set. Just apply it on the inverse graph. And if there's an algorithm for independent set, it will also work on the Clique. Just apply it on the inverse graph. So they can work together to find that algorithm. Okay? So Bob and Carol are kind of happy now. But how about Alice? Alice feels a little out of place because she's not included in the meeting. So Alice and Carol also met up, and Carol shared the good news with Alice. So they talked about Alice's problem about the telecommunications and putting all those monitoring devices. So what is the largest independent set in this graph? So independent set, remember, is Carol's problem, right? So the largest independent set we mentioned was BCEF, right? So that was this one. B, C, E, and F. So those are not connected at all. Now how about for Alice's problem, vertex cover? What is the smallest vertex cover here? What is the smallest number of devices that you can put here such that all the edges are covered? It's actually A and D. Okay? Because if it's A and D, A will cover this edge, A will cover this edge, also this edge, and then D will cover this edge and this edge. So all the edges are covered, right? Now, how are the answers of the two related? Well, here you have BCEF, and then for vertex cover, you have A and D. So it's actually the vertices that are not in the independent set, right? So if it's in the independent set, you take the opposite of that and you get the vertex cover. Okay, does that make sense? So the relation of vertex cover in independent set is that uh, if if you want the smallest vertex cover, all edges are covered in this case, right? And if you remove the nodes of those vertex cover nodes, then there will be no edges anymore because it will take all of the edges that it covered. So if there are no more edges, the remaining nodes are all independent, so there are no connections. So that is the independent set already. Does that make sense? So if we go back here, okay, so let me draw the array, the graph A, E, B, C, D, and F, and probably want to move this down a little bit, E. Okay, and the connections are A to E, D to C, A to D, A to F, and D to F. So we said that the vertex cover was AD, right? So let's that. Vertex cover was AD. If we remove this 2, so what will happen? If we remove this, then what will happen is we remove this, so this edge will be gone, right? This edge will be gone too, right here. Okay, this edge will be gone too. And then if we remove D, then this edge will be gone and this edge will be gone as well. And that uncovered B, C, E, and F without any edges at all. And that's because you removed all the edges, since this one covers all edges, right? So if you remove A and D, you are removing all edges as well. So if you remove all edges, the remaining vertices will be independent of each other, and that would be the biggest independent set since you are taking the smallest vertex cover. Okay, so that is how they are related. So removing the minimum number of nodes will leave you with the maximum number of independent vertices because there are no more edges that remain, right? So all of them has to be not connected to each other. So therefore, the relation of the two is that the smallest vertex cover are the vertices that are not in the largest independent set. Okay, so you take the opposite of the independent set. Okay, so this is another good news because that means that Alice and Carol can work together, and by extension, Alice and Bob and Carol can work together to solve their problems. So we can reduce vertex cover to independent set and independent set to vertex cover. So the good news again is Alice and Carol can work together. So the little bit of good news is that Clique, independent set, and vertex cover are all reducible to each other. Okay, so if there is one algorithm that solves one of their problems, then all three problems are now solvable. So this means that Alice, Bob, Carol can work together. So finding a polynomial time algorithm for one problem also solves the other two. However, there's kind of a good news slash bad news. There are only two things. Either the three problems are tractable, meaning there's a polynomial time algorithm that exists, and if it exists, then all three are okay now because all their problems are solved. Or all three problems are intractable, meaning no polynomial time algorithm exists for all their problems. So that's either good news or bad news because it's all or nothing, right? Either there is one algorithm that will solve it for the three of you, or there really is no algorithm that will solve it for the three of you. So let's take a step back first and figure out what it means to be intractable. If your problem has an exponential number of possible solutions, so you have a lot of possible solutions, just like what we had in the three problems that we had for Alice, Bob, and Carol. So they had, if you brute forced it, it would take them 2 raised to n possible solutions, right? So if a problem has exponential possible solutions, is it automatically intractable? Okay, the answer is no, because there are problems with an exponential number of solutions but has a polynomial time algorithm. So an example of this is the shortest path problem. So you've already encountered this, I think, in your discrete math or your algorithms class. So let's see. For this first graph here, you have 4 vertices and you only have 2 paths, right? So you have the upper path here, 1, and the lower path, 2. So 4 vertices, n, and the path is 2. So number of possible solutions. For 6 vertices, you have 4 paths. So you have the 1 here, 2, 3, 4. Yeah, it's 4 paths. 4 paths in total. And then if you have 8 vertices, you have 8 paths. So you have 1 at the top, 2, 3, 4, and then you have 4. You can take this 5, take this 7, 5, 6, or you could take this 7, or you could take this 8. So there are 8 possible paths, and then for here 10 has 16. So I won't enumerate it anymore, but there's a total of 16 paths. So for n vertices, so you have the 4, 2, and then you have the 6, 8, 10, 4, 8, 16. So the number of paths here, given n as the number of vertices, would be 2 raised to n over 2 minus 1. So what is n over 2 minus 1 in this case? N over 2 minus 1 here is 4 over 2 minus 1. This is 6 over 2 minus 1, 8 over 2 minus 1, 10 over 2 minus 1. So this is 2 minus 1. Okay, this is 2, 4, 8, 16. So 2 minus 1 is just 2. So that is 2 squared. Oh no, 2 minus 1 is 1, not 2. So that's 2 raised to 1, which is equal to 2. This is 3 minus 1 is equal to 2. It's 2 squared equal to 4. You have 4 minus 1 is equal to 3. So that's 2 cubed equal to 8. And then 10 over 2 is 5 minus 1 is 4. So 2 raised to 4 is equal to 16. So that is the form 2 raised to n over 2 minus 1. But this is still exponential, right? So there's an exponential number of solutions for the shortest path problem, because there's an exponential number of paths. So if you check each one to find the shortest one, then yeah, you can find the shortest path. However, even if there are exponential number of possible solutions, there are polynomial time algorithms, like we've seen Dijkstra's algorithm, Bell-Manford algorithm, and other shortest path algorithms in ComSci 142. So it's not the case that if you have an exponential number of possible solutions, it's automatically intractable. because there could exist a polynomial time algorithm for it. Okay? So shortest path problem is tractable. Now, how about this one? If you can only solve the problem so far by using brute force or trying all possibilities, is the problem automatically intractable? So can you claim that the problem is intractable given that you've tried and spent like years trying to solve the problem, but somehow only brute force works so far? So can you claim now that this problem is intractable? It can't be solved in a reasonable amount of time. Well, no, because there could still be a polynomial time algorithm that you haven't discovered yet. Okay, by not knowing it doesn't mean that it does not exist. Okay, maybe you just haven't found out yet. Okay, now which of these two is easier to do? Is it showing tractability or showing intractability? Which one do you think is easier to do? First one or the second one? Well, it's easier to show tractability. Why is that? Because to show that the problem is tractable, you only need to show one polynomial time algorithm and automatically the problem is tractable already. Right? Now, the hard part is actually finding that polynomial time algorithm. But it's easier to show that it is tractable because the only step that you have is finding that polynomial time algorithm. No matter how hard the process is, but there's only one step. Okay, so this one is easier because showing intractability is actually harder because you need to show that no polynomial time algorithm exists. Okay, so not just that this one will not work or this one will not work. You have to show that all algorithms run in at least exponential time. Okay, so it's not just for certain algorithms. You have to show that for any algorithm for this problem, it will run in at least exponential time. So this one is harder because you have to show it for all algorithms. Okay, so now there are two ways that you can do this. First is you can gather evidence. Like you can try to find more people working on similar difficult problems and try to relate your problem via reduction. So you can follow what Alice, Bob, and Carol did, and they found out that their problems were reducible to each other. So you can find people working on similar difficult problems, and if they can't find a polynomial time algorithm either, then the problem could be intractable. But the key here is could be, because the idea behind this is that if there's a lot of people working on it and none of you could find the answer, then it might be intractable, right? That could be the idea. But this one is easier to do, but it's not as convincing because the counter argument is, what if even if there are many people working on this, what if you just haven't found it yet, right? What if there is a polynomial time algorithm? It's just that the person born to discover this is not the person that's supposed to discover this is not born yet. Okay, something like that. So you can do this. You can find friends. You can find colleagues who are working on similar problems and try to relate to them via reduction. But it's not as convincing because although you can kind of convince yourself that yeah, there's a lot of us smart people who are working on it and it's just not working out, so maybe it's intractable, but it's not foolproof basically. So the other one is you actually need to show mathematical proof, right, to show that it's intractable. So you need to show that no matter what kind of clever algorithm you use to solve the problem, it will need at least exponential time. Now this is harder to do because you don't prove this for one or two algorithms, but you need to prove this for all possible algorithms. Okay, that no matter how the algorithm is constructed, it will always take at least exponential time. Okay, this one is harder to do, but at least this is more convincing because it's a mathematical proof. Okay, if you can prove it, then you are really sure now that this problem is intractable. Okay, so those are the two ways that you can show intractability. And that's where we'll end this video for now. Okay, so we talked about undecidability, wherein the focus is on um, decidable versus undecidable problems. Okay, so what can a computer solve or not? Okay, so examples of undecidable problems were the halting problem, the 3n plus 1 problem, equivalence of two programs, specification, and so on. Okay, and then for intractability, it focused on whether the problem, which is assumed to be solvable, okay, does the algorithm run in a reasonable amount of time or polynomial time, or is it unreasonable or exponential? Okay, so is it tractable or not? So that was the focus of this video. Now in the next video, which is our last set of topics, we will talk about the P versus NP problem. Okay, we'll talk about NP complete problems and how to cope with NP completeness. So this will be the last lecture for this course. Okay, so that's it for this video. If you have any questions, please don't hesitate to ask, and I will see you in the next one.